Hello GATE aspirants, welcome to GATE Chemical Solution channel. This is a 2-mark fluid mechanics question in the year 2020 GATE question paper. Please read the question very carefully and identify what is given and what we have to find out. So initially we will see the concept for this problem, then we will go for the problem solution. If you are well aware of the concept, you can skip the concept explanation part. Okay, this comes under incompressible flow in a pipes and channels. So in that we will see the shear stress and skin friction pipes. So for that, consider a horizontal tube or pipe in which the fluid is flowing. The fluid is steady fluid, the flow is steady flow and fully developed, and density of the fluid is constant. Okay, visualize a disc like fluid element of radius r and length dl. Okay, it is concentric with the axis of the tube or pipe. Okay, so if you see on the figure, the upstream pressure is P and the downstream pressure is P plus dP. Okay, so say viscosity and the shear stress will oppose the flow of this fluid, right, because of the viscosity. Clear? By doing momentum balance over a fluid element, so sum of the forces equal to the increased amount of the momentum, right? So here we have mentioned that the flow is fully developed flow. It means its velocity at the entrance equal velocity at the existence, only it is varying along the length radius of the pipe, right? So this is the velocity profile in the pipes. Okay, so here it is 0, here it is maximum, only it is varying along with the radius, right? So along the length it will be constant, length of the element. So since it is fully developed, beta A equal to beta B. So what are the forces which are acting? The pressure force. So the inward and outward forces, pressure forces on the element, and wall shear and gravitational force. These are the forces actually acting. But since the pipe is a horizontal pipe, the gravitational force will be 0. Okay, so since we are assuming that it is a horizontal pipe of a circular cross section, SA equal to SB, that equal to pi r square. Okay, so PA equal to P and PB equal to P plus dP. So by substituting all these terms in the equation 2, so we will get the expression like this. So this term will cancel by simplifying this expression, and this term will get cancelled. So this is shear force. So we know shear stress tau equal to shear force or wall force divided by area. Okay, so from this surface area, from this we will write 2 pi r dl of the visualized disc like fluid element. Okay, so by dividing this expression by pi r square dl, we will get this equation, and for entire cross section we are by taking this one for a fluid element, this is the expression. By taking the entire cross section, this is the expression. So in a steady flow, either laminar or turbulent, the pressure drop at a given cross section of the stream tube is constant. So for a given cross section means radius is constant. So for a given cross section of the tube, the dP by dl is independent of the radius. Okay, it is constant in the for a given cross sectional area. So dP by dl is constant. Because of that, for taking the entire cross section of the area, cross section of the tube, this dP by dl at the, since radius of the tube at the tube wall is Rw, right? So at the wall, the shear stress is tau W. Okay, the same expression will be given like this for entire cross section of the tube. So from this equation 3 and 4, so by subtracting 4 in 3, we will get tau W by Rw equal to tau by R. Clear? Only this relation is valid for laminar or turbulent. For steady flow, any flow pattern it will be applicable. Clear? This expression tau W by Rw equal to tau by R. Okay, so from this tau and R are linearly related, right? So if R equal to 0, tau equal to 0. So this distribution will be given as like This is the shear stress distribution along the radius of the pipe. Here it is 0 at the center, the shear stress will be 0 and it is maximum at the wall. Okay, this is the linear relationship between tau and R applies in both laminar and turbulent and both Newtonian non-Newtonian fluids. This relation is valid for both laminar and turbulent as well as Newtonian and non-Newtonian fluids. Clear? So if we consider the Bernoulli's equation, so by incorporating the fluid friction and kinetic energy factor, kinetic energy correction factor, this is the equation. Okay, between two sections, section A and section B, entrance and exit, let's say. So this is the relation. So in our particular case where we have assumed it is the flow is a fully developed flow, it means velocity at inlet section and outlet section are the same. So this term and this term will be equal, it will be get cancelled, and the pipe is horizontal, so Z term will be also this Z and there is no elevation, so these two terms also will be 0. Okay, here this is the fluid friction incorporated in this Bernoulli's equation. So from this Pa minus Pb by rho equal to Hf. Okay, here only the friction, the whatever may be the pressure drop resulted here, that is because of the fluid friction of skin friction between the fluid and solid boundary. Because of that friction only this pressure drop will be resulted. Okay, here only friction is the skin friction, that is unseparated boundary layer. If there is a boundary layer separation takes place, in that case form friction also will be incorporating. Okay, so that's why the pressure drop resulted here is the only because of the skin friction between the fluid and solid boundary. So that is delta Ps by rho equal to Hfs. This S indicates the skin friction. So for a definite length L of the pipe, equation 4 becomes, we have written dP by dL plus tau W by RW, 2 tau W by RW equal to 0, right? From that expression, by integrating over a definite length of the pipe, since delta P is independent of the radius, so we have integrated over the given boundaries, we will get this expression. Clear? So 2 tau W by RW, length of the pipe from 0 to definite length, that equal to minus initial to final limits Pb minus Pa, from this Pa minus Pb, that is nothing but Ps. Okay, delta Ps. So delta Ps equal to 2 tau W by RW into L, that equal to 4 tau W by D. This RW is written in terms of the diameter of the pipe, so that equal to 4 tau W by D into L. Okay, so this equating in terms of friction, skin friction, Hfs equal to, since delta Ps by rho equal to Hfs, right? So here Hfs equal to delta Ps into rho, that 4 tau W by rho into D into L. So this equation is applicable for both laminar and turbulent and Newtonian and non-Newtonian fluids also. Clear? So this equation 10 is applicable for both laminar and turbulent, Newtonian and non-Newtonian fluids. Clear? So till now we have discussed the concept related to laminar or turbulent flow and Newtonian non-Newtonian fluids. Specifically now we will see the for laminar flow of Newtonian fluids. So this concept is given, the description for this concept will be given in the description form. The concept explanation related to this part will be given, the link is given in the description, so we will go through that one. So from this you will get average velocity equation expression like that. After integrating we will get this equation. Okay, from this, so V bar can be written as tau W RW divided by 4 mu, right? Okay, so from the equation 9, by substituting tau W is equal to delta PSD by 4L, in equation 11 we will get V bar equal to 4 delta PSD by 4L into RW by 4 mu. Okay, if we convert this also in terms of diameter, we will get delta ps d square divided by 32 mu l. Okay, this delta ps equal to 32 mu l v bar by d square. Equation number 12 is, that is delta ps equal to 32 mu l v bar by d square. Okay, this is called as a Hagen-Faisali's equation. This is applicable for study incompressible laminar flow of fully developed Newtonian fluids. Clear? Okay. So all of you well aware of this equation, right? It is a very familiar equation, that is delta ps equal to skin pressure drop resulted because of the skin friction in steady flow of incompressible laminar flow of fully developed Newtonian fluids is 32 mu l v bar by d square. Clear? So from this equation 12 and equation 9 we can equate delta ps. Okay, so that is from equation number 9, delta ps equal to 4 tau w by d into l equal to, from this equation number 12, delta ps equal to 32 mu l v bar by d square, right? So by simplifying this one, we will get tau w equal to 8 mu v bar by d. Clear? Okay, this is the concept related to required for our problem solution. We will see the problem solution now. So if you look at the problem, it is given that it's a steady flow laminar fully developed incompressible Newtonian fluid flowing in a two horizontal pipes of circular cross section. That is the given in the problem. That is, let's say this is the pipe 1 and this is the pipe 2, and also given that the volumetric flow rates in both the pipes will be equal. That is, let's say Q dot is the volumetric flow rate. So Qi dot is the volumetric flow rate in pipe 1. So similarity is in pipe 2. So and also given diameter of the pipe 2 equal to 2 times the diameter of the pipe 1. So and they have asked us to calculate what is the shear stress at the wall of the pipe 1 to the shear stress at the wall of the pipe 2. This ratio we have to find out. Clear? So from this, from the derivation previously I have done from the concept point of view. So tau w equal to 8 mu v bar by d, right? Actually, if the pressure is constant, we can from the given data we can directly consider the Hagen-Faisalian equation, that is delta ps equal to 32 mu v bar l divided by d square, but they have not mentioned that pressure is constant. Actually, pressure for a steady flow is either it is laminar or turbulent. It is for a given cross section, it is constant for a single pipe. Okay, but here the two different pipes are we are taking, so we cannot take pressure as the constant in both the pipes, but the fluid is same, fluid is flowing in both the pipes. So in that case, so we have to consider only this equation. Okay, so the remembering this equation is a very difficult thing, that's why I have given in the derivation. Okay, most of the cases generally they will ask based on the pressure constant only. Okay, even though if the pressure constant also we can replace V bar in terms of volumetric flow rate. Okay, so they have given V bar can be written as in terms of volumetric flow rate per unit area. Okay, cross sectional area of the pipe is circular cross section, that is pi by 4 d square. Okay, by substituting V bar term in this equation we will get this one. So by simplifying 32, since same the fluid is moving in both the pipes, right? So viscosity also constant and this is also constant term. So volumetric flow rate in both the pipes also constant. Okay, the only varying term is diameter of the pipes. Okay, so tau w is proportional to 1 by d cube. So tau w1 by tau w2 equal to d2 cube divided by d1 cube. So tau w1 divided by tau w2 equal to d2 cube divided by d1 cube. So d2 is again 2 times the d1, right? So by substituting this one and this one it can get cancelled, we will get the 8. So tau w1 divided by tau w2 equal to 8. That is option D is the correct answer. Clear? I hope you have understand the problem and concept. So if you have any doubts, please ask in the comment section. If you like the video, subscribe and share. Thank you.